Yeah, hello, and thanks to Roman for the invitation and for the kind introduction. I'm really happy to be here and to speak today. This is Imre-Lakatos. You have all seen this picture, I suppose. I never met Lakatos personally, of course. I was only 5 years old when he died. I also didn't learn much about Lakatos when I studied. I studied with convinced Popperians for my master, and then I moved to the University of Constance to study with Paul Heuningen-Hühne, who was a big fan and acquaintance of Kuhn and Feierabend, so I somehow missed Lakatos here. But my connection to Lakatos is mainly that I worked for a couple of years in the Lakatos building at Lakatos University, that is here, and I learned more about Lakatos also through two gentlemen. They are here, Colin Howson and John Worrall, who were both students of Lakatos. And to prepare for this talk, I read a bit around, and there are a number of volumes dedicated to Lakatos, and in one of these volumes, John Worrall added a little autobiographical note, and he said about Lakatos that he had none of the German professor about him. That shocked me a little, because I am a German professor, but what he meant here is he said immediately afterwards that Lakatos was genuinely delighted when John Worrall or Elie Saha or Colin Howson found good criticisms of something he had written. And immediately before that, he also said a few other things about Lakatos, some not so nice things and some nicer ones. He said, for example, that Lakatos could be infuriating, he could be a bully, he wanted to control every aspect of the life of his apprentices, vetting potential girlfriends for social acceptability, deliberately telephoning and keeping him talking for hours at times when he knew that he wanted to be out partying. It's quite entertaining, as one expects from John, and I recommend you to read this if you like. So what did Lakatos do? Lakatos is mainly famous for two things: for his philosophy of mathematics in proofs and refutations from 1976, so posthumously published, but before in a number of BJPS articles, and for his philosophy of science, in particular his methodology of scientific research programs, which he mainly developed in two longer papers: Falsification and the Methodology of Scientific Research Programs, which was published in this famous Lakatos-Mascreff volume, and History of Science and its Rational Reconstructions in a volume that Colin Howson edited. Not least in response to Kuhn and Popper, Lakatos was interested in major and highly interrelated issues in the philosophy of science: the demarcation problem, the rationality and objectivity of science, theory change, and scientific progress. Some of these issues, especially the demarcation problem, are not very much discussed these days, although it seems that philosophers of science should have something to say about them these days. There is a recent attempt by Paul Heuningen-Hühne, which you might have seen. For Lakatos, and now I say a few more words about what he achieved, the philosophy of science provides normative methodologies in terms of which historians reconstruct the internal history and thereby provide a rational explanation of the growth of objective knowledge. It also provides it also allows us to compare competing methodologies in the light of these normative standards, and any rational reconstruction of history needs to be supplemented by an empirical, socio-psychological external history. So these are the words you have probably all seen: internal history, external history, and so forth. Lakatos was an objectivist and an anti-inductivist, though of a less rigorous kind than Popper. Lakatos, along with Popper, Kuhn, and Feyerabend and other followers after them, rejected the general need or desirability of formalizing scientific discourse for philosophical analysis. And if you look at these remarks, it's pretty clear that Lakatos was, unlike me, not exactly a Bayesian. So, what's Lakatos' relationship to Bayesians and to Bayesianism? Well, at least two of his students, Hausen and Urbach, became leading Bayesian philosophers of science. And another, Worrall, sympathizes at least somewhat with Bayesianism, as suggested, for example, by his essay Kuhn, Bayes, and Theory Choice, which he published in 2000. Of course, he says that he has all sorts of objections, and it's not objective enough, and the priors are bad, and so on and so forth. But he has sympathies, some sympathies for Bayesianism. I fear, however, that all this would not have convinced Lakatos, nor would he have been convinced by the Bayesian solution to the Duhem problem proposed by John Dorling and popularized by Hausen, Urbach, and others. Deborah Mayo, in her Lakatos award-winning book, Error and the Growth of Experimental Knowledge, called it Dorling's little homework problem or so, to assign priors so that things work out in the way they should, or they did actually work out. So, nevertheless, I would like to argue that Bayesianism, when properly understood, is a fine example of an interdisciplinary scientific research program that can be of real use to science, which is one of the important tasks of philosophy of science, not to mention the big questions about rationality and objectivity that we should sometimes be concerned with as well. That is, I think that Lakatos is wrong, at least with regard to contemporary Bayesianism, when he writes that probabilism has never generated a program of historiographical reconstruction. It has never emerged from grappling unsuccessfully with the very problems it created. And as an epistemological program, it has been degenerating for a long time. As a historiographical program, it never even started, so that's pretty devastating. So I'm not so much concerned with historiographical reconstructions, but I will say a bit more about the role of history of science and its implications for the philosophy of science later. So here's the plan. I shortly introduce Bayesianism. I suppose you're familiar with that. I then address two problems. So I think that there's lots of problems, and one can sort of try to figure out what's in the hardcore, what's in the protective belt, if one wants to give such a reconstruction. And I think one can make a nice case that it's really a progressive research program, pretty much along the lines of Lakatos. So I'll basically talk about problems. Some problems I think are already solved, others will be solved soon or so, I hope. So that's the plan of the talk, and I start with standard Bayesianism. It's a theory about the statics and dynamics of partial beliefs. Its a starting point is the psychological truism that we believe different contingent propositions more or less strongly. We assign different degrees of belief to them. And to make the concept of degree of belief more precise, what one needs is a calculus to combine different degrees of belief. One needs an algorithm to update degrees of belief, and a normative justification for these two items. And that's exactly what Bayesianism provides us with. So let's see how this works for the static and dynamical part of Bayesianism, and in doing so I will present what's typically taken to be in the hardcore of Bayesianism. So to begin with the static part, Bayesians identify degrees of belief with probabilities. That is, rational degrees of belief of an agent at a certain time have to satisfy the axioms of probability theory. There are pragmatic and epistemic justifications for that, but I'm not going into that. The dynamic part is basically about how to change one's beliefs, and one way that some people consider to be in the hard core of Bayesianism, therefore the name is Bayes' theorem, I don't think so, as I will later argue, but Bayes' theorem is basically a way of updating one's beliefs. Once we learn that one of the propositions that we entertain in the algebra of propositions we entertain is true, then we apply this recipe and we get the new degrees of beliefs. There are ways of dealing with information which is not fully certain, or which the agent doesn't consider to be fully certain, and all sorts of other things can be said about this. I here only want to talk about the one major application of Bayesianism, traditionally the only application, but now there is a host of different applications of Bayesianism. I'm speaking of confirmation theory, and here the typical scenario is that one considers evidence which is considered to be direct evidence for some hypothesis, so it's a deductive or inductive consequence of this proposition that we want to test or evaluate. One can then, after learning that the evidence is the case, update one's probability of the hypothesis, and if it's greater than the prior probability, one has confirmation. Otherwise, one has disconfirmation. One can also study more complicated scenarios involving more propositions, involving auxiliary hypotheses, and so forth. But most standard applications just use two propositions, H and E. Of course, Bayesianism being a scientific research program is not without problems. It's also sailing in some sea of anomalies, some ocean of anomalies, as Lakatos would put it, and people from Pittsburgh and elsewhere have made an effort to point all of them out. I think that some of these problems are just modeling challenges, and others perhaps point to a better theory or research program. And indeed, there are alternative research programs which should, in my view, also be studied to compare better with Bayesianism. So I'm not too concerned about all that, and I think that much progress can be made here in developing that program. I would like to identify three further problems which haven't been identified as far as I know by the people from Pittsburgh. One is the problem of non-empirical evidence. So the problem is the following. Standard Bayesianism assumes that the evidence is direct, as I explained before, in the sense that it's a deductive or inductive consequence of the theory under consideration. However, this may not always be the case. Some evidence may be non-empirical, as it's sometimes used. I think the term indirect is better. There is actually a lively debate about all this in the methodology of fundamental physics, in particular, where direct evidence is scarce, and people would nevertheless like to maintain that the theories they are entertaining are scientific, and so there should be some evidence or so. So what could this evidence be? And I give two examples. One example that people came up with is the so-called no alternatives argument. The idea here is that we don't have direct empirical evidence, but what we have is people who try to find an alternative to the theory under consideration, in particular in this case string theory or so. Yeah, and now these people are of course all very, very smart, and they work very hard, and they failed. Yeah, they didn't come up with an alternative to string theory, and so given that they observed, or that we observe the fact about the scientific community that it failed to find an alternative to string theory, some people take this to be a confirmation of string theory. The question is, does this argument go through? Is this a good argument or so? Yeah? Another one is analog simulation. Here the question is, can we test predictions about a system which we can't empirically access, like a black hole Hawking radiation by experimenting on a different physical system. So people study Bose-Einstein condensates and they create the analogous effect of Hawking radiation in this Bose-Einstein condensate. And the question is this, the evidence about the Bose-Einstein condensate, is this evidence for the existence of Hawking radiation in black holes? It's an interesting question. And of course, it's also not direct evidence. The question is, does it work or not? And these are questions where philosophers also contribute to the debate, and it turns out that this can be captured in the Bayesian framework. So in both cases, the elect evidence is indirect and in this sense non-empirical. It would be fantastic, of course, to have such ways of indirect confirmation, but it's not at all clear whether it's possible. And if it's in principle possible to have non-empirical confirmation, under which conditions is it possible? Now, it's interesting to note that traditional theories like HD confirmation or Popper's falsificationism, I guess also Lakatos' methodology of scientific research programs, would dismiss such evidence right from the beginning or so, because it's not a deductive or inductive consequence of the tested hypothesis or so. But I think that this inference is too quick. It may well turn out that there is non-empirical evidence, and it should not be part of the basic assumptions of a confirmation or corroboration theory one uses, that it doesn't exist. So I think it's simply a question to explore, and the Bayesian framework is rich enough to explore this question and to investigate under which conditions non-empirical or indirect evidence can function. So that's problem number one. Number two, new types of evidence. Standard Bayesianism assumes that the evidence is propositional. However, there may be evidence which does not prompt a shift of the probability of one of the propositions in the algebra. Some evidence may be non-propositional. Now, again, it seems to be too restrictive to only consider propositional evidence. There may be other types of learning experiences that prompt us to change our beliefs. And the question then is, can this or how can this be modeled in the Bayesian framework? Two examples. One is structural evidence. The agent may learn, for example, that the underlying causal network of a set of propositions is such and such. That's nothing one can condition on. And the second example is indicative conditionals. The agent may learn an indicative conditional of the form if A then B. And it turns out that in some cases this prompts us to change our beliefs. So how can this be modeled? Again, it's difficult to just apply conditionalization and get something out. So it's not clear whether these learning experiences can be modeled by conditioning on a proposition from the algebra. In the case of structural evidence, one may not want to assume that the agent has meta-beliefs about the other propositions in her algebra. And even if she had, how should one update on them? In the case of indicative conditionals, it's controversial whether conditioning on the corresponding material conditional works. Things become especially complicated when the conditional is not strict. Now, we will focus on learning indicative conditionals and see that the distance-based approach to Bayesianism, which uses a so-called diachronic norm called conservatism, has the resources to analyze cases of non-propositional evidence. Here is shortly a third problem. Standard Bayesianism assumes that the learned proposition is already on the agent's radar. It's expected and has a prior probability. However, this may not always be the case. Some evidence may be genuinely new. Now, it's very plausible that agents have prior beliefs about all possible kinds of evidence they may learn. Here are four examples. Testimony is an example. A bystander gives a testimony about a murder case. Here, it's not plausible that the policeman had any prior expectations about this testimony. Or if you are in an argumentation situation, we are debating and you make a new argument which I didn't anticipate. theory change is an example. A new theory shows up, and it's not plausible that the agent expected it somehow, let alone that she assigned a prior probability to it. It is also not plausible that the new theory emerged from the catch-all of the old theory, which may work sometimes. Relatedly, the discussion about novel predictions may profit from a solution of this problem. So it may be interesting to analyze, once one has such a theory, to analyze the notion of novel predictions or so, and see whether they really give such a big boost to confirmation or so. Now, it's a serious restriction of the Bayesian framework that it requests that the algebra of propositions is kept fixed. At the same time, it's a big advantage of logical frameworks, such as the AGM model of belief revision, that they can deal with these cases. It will be interesting to make the literature of awareness and the work of John Williamson, who did some interesting stuff here, useful for the discussion here in the philosophy of science. I will now shortly outline how the first two problems work, and I will not say much about the last problem. Yeah? But what I would like to stress here is that if, as I would like to argue, Bayesianism is something like a scientific research program or so, it's also negotiable what's in the hardcore and what's in the protective belt. Yeah? So I think, for example, that Bayes' theorem, this updating rule conditionalization, is not in the hardcore or so. So it is some more general principle is in the hardcore, and I think that that's totally okay. So let me move on to non-empirical evidence. So I would like to argue that Bayesianism has the resources to model such confirmation scenarios, and the idea is simply that if there is no direct connection between H and E, the hypothesis and the evidence or so, and they are nevertheless correlated, then we have to find some common cause variable that screens them the correlations off and correlates the two variables. So the big thing is then for a particular scenario or so to find out what this common cause variable is. Of course, one can also study other network structures, and Bayesianism has, as I said, the resources to do all that. In the case of the no alternatives argument, we have a hypothesis, namely that a certain theory satisfies various desirable conditions. And we have the observation about the scientific community that despite a lot of effort, the scientific community has not yet found an alternative to H. Hence, we have one reason in support of H. The question then is, how good are these arguments, these no alternatives arguments, and under which conditions, if any, do they apply? That problem can be addressed or solved by introducing three variables, T for the theory, F for this evidence, and Y, that's the common cause variable. It's a variable that has n values, and these values there are exactly I hypotheses which explain the data and fulfill the conditions that the hypothesis in question satisfies. And it's easy to see that Y does screen off F and T, and one can then show that under fairly general conditions, F indeed confirms H. So the no alternatives argument works. And I would like to stress that this qualitative conclusion follows from the premises without completely specifying the prior. So I actually think that much can be said about confirmation scenarios or so without arguing whether the prior of a certain theory in the 17th century or so was 0.62 or 0.74 or something. Yeah? So that follows simply from general considerations, and the conclusion also follows from three apparently plausible premises. One assumption is perhaps the weakest. It's the assumption that we are not certain, or the agent is not certain about how many alternatives there actually are to a given theory. That may sound strange for someone who knows about the underdetermination thesis, which suggests perhaps that there are always infinitely many alternatives to a given theory, so perhaps one should set P of y infinity is 1, but if that is so, then the correlation is gone and the argument doesn't go through. So someone who wants to make the no alternatives argument has to say something here, and Richard David, who is a defender of this no alternatives argument, does so. Analog simulation, yeah, this black hole Hawking radiation thing can be analyzed in a similar way. So the idea here is basically that one adds other active variables, variables about which scientists have beliefs, yeah, beyond H and E, yeah, like how many alternatives are there and so forth, and the causal structure of the network is also doing some work here. Yeah, and there's many other applications that can be studied with this methodology. Let me now move on and talk about the second problem, new types of evidence. And here I will focus on learning a conditional. Igor Duven wrote a book about this, and he came up with lots of really nice examples that are sort of a challenge to model. One is the ski trip example. Harry sees his friend Sue buying a skiing outfit. This surprises him a bit because he did not know of any plans of hers to go on a skiing trip. He knows that she recently had an important exam and thinks it's unlikely that she passed. Then he meets Tom, his best friend and also a friend of Sue, who is just on his way to Sue to hear whether she passed the exam, and who tells him, if Sue passed the exam, then her father will take her on a skiing vacation. Recalling his earlier observation, Harry now comes to find it more likely that Sue passed the exam. So it's a nice example, it's a challenge. Yeah, how can this be modeled in the Bayesian framework if we agree with this intuition that the probability that she passed the exam goes up? So how can this be done? Well, there are three variables at work. E, Sue passed the exam. S, Sue is invited on a ski trip. And B, Sue buys a skiing outfit. And what actually happens here, if you look at the example, we learn all sorts of qualitative things about the probabilities and conditional probabilities from the story, and we also learn that the agent learns B, yeah, sees her buying a skiing outfit, and if E, then S. Yeah. Now, it actually turns out that if one, in this example here, conditionalizes on B and the material conditional E implies S, then one can show that the probability of E increases. Only learning the conditional would lower the probability, that's the Popper-Miller result, but also learning B pushes it up, so it's important that the agent also learns B. So one doesn't need any fancy tricks or mathematics here to get these cases actually done. It just works with the material conditional, never mind whether it has problems or not. Yeah? Things get more interesting if the conditional is non-extreme, like in the Judy Benjamin example or so, yeah, where it's not for sure that the conditional obtains. Yeah? And in cases where the conditional is uttered by a partially reliable information source. So yeah, that is also typically the case, and certainly something a Bayesian should consider. And this second problem is totally unsolved as far as I know, and the first problem can be dealt with by introducing what's called the distance-based approach, which is basically a generalization in a certain sense of conditionalization or Jeffrey conditionalization. The idea is very simple. An agent entertains prior beliefs about a number of propositions. Then the agent learns some new information, which are simply constraints, then probabilistic constraints on the new probability distribution, Q. Yeah? And then the agent makes sure that the distance between the old distribution and the new distribution satisfying the constraints is as small as possible. Yeah? That's the idea. Yeah? So without the constraints, of course, the new distribution would be the old, but there are these constraints which have to be satisfied. So then turns out that if the agent entertains propositions H and E, and the constraint is Q of E is 1, then by using this machinery here, one gets space theorem out or so. And the nice thing about the machinery here is that it can be applied also to other constraints, yeah, not only constraints where we learn the new probability of a proposition. All this, of course, presupposes that we have some kind of measure that allows us to measure the distance between two probability distributions. So how can this be done? Here is a class of distance functions, so-called F-divergencies. One of the F-divergencies is the well-known Kullback-Leibler divergence from information theory. It turns out that whatever F-divergence one chooses, so whatever convex function F here one chooses, one always gets Jeffrey conditionalization out if one just considers two propositions and learns that the probability of one of them somehow shifts around. So that I take to be an interesting result, and that I take to be a reason why one should focus on F-divergencies, because Jeffrey conditionalization seems a reasonable thing to do. However, in certain cases, it depends on which F-divergence one chooses, and then there is this problem how to choose amongst different F-divergencies. So that's a bigger research program, which is still ongoing, sort of a sub-research program within the bigger Bayesian research program, and it's a program that also involves empirical studies, I think, and normative considerations. So the question is, how should we actually update in realistic situations when we learn things like conditionals or so? So one way to argue is that we want to also be satisfying the norms of epistemic utility theory. This account favors so-called Bregman divergences, and it turns out that there is only one divergence, which is a Bregman divergence, and an F divergence, which is the inverse Kullback-Leibler divergence. So if we want those two norms, yeah, epistemic utilities or minimizing inaccuracy, and if we want to be conservative along the lines of F divergences, then we have to go for the inverse Kullback-Leibler divergence. If we don't want that, then one can try to come up with other diachronic norms which minimize or restrict the space of possible F divergences, or one can simply do experiments, Coxi experiments or so, and see how real people update, and maybe one finds some patterns or so and do that. So I think at the moment the best thing to do is to do everything. I mean, number 2 and number 3, but I don't have an answer to number 2 yet. So that is an ongoing research program, yeah. But as I said before, the point I want to make here is that it somehow suggests that, I mean, in the light of new data or so, yeah, now we also sometimes learn conditionals or so, can't be modeled with conditionalization or so, yeah. So that suggests that the Bayesian research program can be fully intact. It's just that we have to move conditionalization from the hardcore to the protective belt, or replace it by something more general in the hardcore. And I think there is nothing spectacular or so about it. It's just what happens. Now, in the last couple of minutes of the talk, I want to discuss much shorter some further problems and questions which can be addressed and which should be addressed, I think. One, I talked already about that before, is the problem of old evidence, which is another anomaly of the Bayesian research program, and many people thought that it's a big killer or so. I don't think so. I think it's at best a modeling challenge that can be met. So what's the problem? The problem is that if an agent assigns a prior probability of 1 to the evidence, that is, if P of E is 1, then E cannot be learned, and it therefore does not even make sense to apply any updating rule or so, because nothing really changed. In particular, this means that old evidence, that is, evidence assigned a prior probability of 1, cannot confirm a hypothesis, which is contrary to the scientific practice, as Jacques has pointed out. Now, there are various ways out here. Some people like Colin Howson deny that in such cases P of E is 1, so they come up with some kind of counterfactual approach, and other people argue that the agent doesn't actually learn E in such cases, but something else. In particular, Garber proposed that what the agent actually learns is that the hypothesis implies the evidence, and then we somehow have to update on that, and people found out ways how to do this. Yeah? Glimmer already proposed and insightfully discussed and also rejected both of these ways of addressing this anomaly of the Bayesian research program. I have my own solution, which I think works, which considers actually two additional variables. The variable x, that h explains E, but it's important in my view to consider that the agent also has beliefs about another variable y, namely the variable h's best competitor explains E. Yeah? And if one then comes up with reasonable conditions that x and y satisfy, then one can show that old evidence can actually confirm. So that's a debate. As I said, it may also depend on the context or so one considers or so, but basically the old evidence is a modeling challenge and not a big issue. Then there is the problem of scientific theory change, and a number of people like Ehrman and Salmon and also Worrell have explored Bayesian accounts of Kuhn's theory of a theory change. In this respect, they didn't fully succeed, also because they did not consider all aspects of Kuhn's theory. So incommensurability is usually only mentioned in the last sentence, for example, by Ehrman or so, but maybe it's ridiculous or so, but for Kuhn it was important, and so these accounts don't address this. Lakatos aimed at a rational and objectivist account of theory change, but argued that there is no instant rationality, as he called it. We can provide such an account only after the fact, when the internal history is in the form of a rational reconstruction. This, of course, invited Feyerabend to write, if you are permitted to wait, why not wait a little longer? And he welcomed Lakatos as a fellow anarchist. Given that theory construction takes place in the realm of uncertainty and that the problem of induction has not been solved, I think it is good not to have an algorithm, as Kuhn wanted, to help us decide once and for all when to abandon a given theory. At the same time, I think that an individual scientist can rationally decide whether to go on and further explore the theory. This is rational even if the theory is in trouble. Note that Lakatos taught us that every research program develops in a notion of anomalies. If, for example, the scientist holds the additional belief, X, there is a model within a given research program or paradigm that accounts for the evidence. Yeah? So you failed, yeah? You tried to come up with a model that accounts for it, but you still believe that it's more likely that you are just not smart enough and someone also will find something. This belief is, of course, updated, and if it always doesn't work and so forth, it goes down, and at some point the scientist decides and the scientific community decides to give up the theory, and eventually it disappears also. So I think some such account can be developed, and I would also like to make things a bit more ambitious here and develop these ideas further into a coherent hist that is decidedly anti-foundationalist Bayesian philosophy of science, which I argue and Colin is certainly on my side here, should have the right mix of objective and subjective elements or so. So that's very quick, and I said this is all just touching on something, but I think that Bayesianism has the resources to make some progress here if one does it properly. I skip over this. It's clear that Bayesianism is in the first place a theory of individual rationality or so, but if Kuhn and others are right, then science is certainly a collective, a group phenomenon, so we need to scale it up somehow to groups. There are interesting questions to ask, there is interesting work already, but of course all this is not as much developed yet as the individualist Bayesian account or so. But I don't see a principal problem here to go on with this. Finally, I want to say something about the role of the history of science. In the work of Lakatos and his followers, the history of science and the rational reconstruction of episodes from it plays an important role, much more so than in the work of Popper. This makes sense for a topic such as theory change. More generally, however, the history of science may provide evidence against bold philosophical claims, and examples from the history of science can illustrate philosophical claims and inspire philosophical inquiry. So that's all good and fine. However, I would like to make three critical points. The first is that the history of science focuses on episodes that are not typical or so. Yeah? So if you look at what Lorden and all these people did, is they somehow seem to disregard that at least 80% of science was done after 1950. So if you want to philosophically understand science or so, it makes sense to focus much more on contemporary science. I know that these things are controversial or so, but I'd like to make this point in this connection to defend my approach here. Second, there is no methodology for providing positive philosophical claims based on the history of science. I think this is really one of the major problems in the whole debate and in the integrated history and philosophy of science movement. It would be really nice to have a positive methodology to inductively generalize something or so. And I would like to discuss this further, but what I see is a history alone just doesn't do the job, and I think what we need is we need to combine it with more general theories like Bayesianism or whatever, and integrate those really. And third, the history of science is blind to normative questions. That's of course also implied by this famous quote by Lakatos: "History of science without philosophy of science is blind." So Lakatos knew all that, yeah. But if history is just descriptive as it's practiced by some historians of science and providing us with all sorts of boring details about certain things or so, then it would, I think, something is needed, a more philosophical outlook is needed, and that. So I think the solution for all this is that one needs to properly integrate normative and empirical considerations, and I would urge that these empirical considerations should not only come from the history of science, but mostly from a study of actual science, because, again, most science has been done in the last 5 weeks or something. Yeah? If you look at the curve of the production of science. Anyway, that was it. Here are my conclusions. The first lesson I would like to draw is that Bayesianism is a progressive scientific research program. It's actually an interdisciplinary research program, as Bayesianism is not only flourishing in philosophy, but also in cognitive science. Some people call it the new paradigm here, Oxford Chater, people around the corner. It's an important research program in neuroscience. Yeah, Carl Friston also around the corner with the Bayesian brain and the free energy principle, and Bayesianism plays an important role in artificial intelligence. I have argued that it's negotiable what is in the hardcore without giving up the whole research program. What is in the hardcore or in the protective belt is not fixed for all time. The Bayesian research program is progressive as it successfully addresses various anomalies, such as the old evidence problem, and it manages to solve new problems. Compared to purely scientific research programs, Bayesianism is special as it involves normativity, and that gives some interesting questions to think about here. More needs to be done to make philosophically interesting new predictions. Addressing Lakatos' major field of study, scientific theory change, is clearly an open field of studies, but I think that the tools are there to do so. Thanks for your time.